as requested, here are an overview of the notes from 6.3, Part 1, where we're talking about volumes of revolution. And anytime we're talking about revolution, we're talking about spinning in a circle. So if a region in a plane is revolved about a line, the resulting solid is a solid of revolution, and the line is called the axis of revolution. We will begin by looking at the disks, which are formed by rotating a rectangle about the axis adjacent to one side of the axis. So here's our rectangle, which each problem we do, we're going to draw in a representative rectangle. And what we're doing is we are spinning it about its axis of revolution. And what you get when you spin a rectangle around a line, you get a disk. And a disk, what we care about is the volume. So we have a bunch of circles added up over the width. So to find the area of a circle, we just do pi r squared. So the volume for our disk is pi r squared, there's our circle, times the width. So r is the radius of the disk, and w is the width. We can use the volume of a disk to find the volume of a general solid of revolution, and we can consider the solid formed by revolving the plane around the x-axis. So instead of just a circle, what happens if we have a curve where it has a start point A and an end point B, and we spin the whole thing around the axis of revolution? Well, in this case, we're going to have individual rectangles of different heights that we will be summing up to find the volume. And what we can do is in each one of these individual rectangles that we have, we are summing up that width, where the width is just the change in the x, and the radius would be the height of that curve. And what we do is we sum up all of these disks of different widths and different heights, and we get the volume of this solid. So to determine the volume of this solid, we do pi times our radius function squared. So instead of just a constant radius, now our radius is a function of our bounded region times the individual width of a disk. And so if we are approximating the width, all we do is we sum up all of these individual disks. And so we use sigma. We have pi r squared times the width. If we add up each individual disk, we will get the total volume. Well, as we've seen multiple times now, that as delta x approaches 0, so the width shrinks, or as the number of disks increases up to infinity, so if n goes to infinity, then this sum formula, just like we saw before, turns into the integral. So the volume of our solid is what we say pi integral from a to b of our radius function squared dx. Now it doesn't always have to be in terms of x. So the way to think about this, if we have a horizontal axis of revolution, or if our rectangle is perpendicular to the x-axis, everything will be in terms of x. And we'll say the integral from a to b of r of x squared dx. And notice the r of x and the dx match. If we have a vertical axis of revolution, so instead of revolving around a horizontal line, let's say we spin around a vertical line, then everything is going to be in terms of y. So our representative rectangle will be perpendicular to the vertical line, or perpendicular to the y-axis in this case. And as we see, the integral, we'll say two different versions, c to d, because we already used a and b, r of y squared dy. Notice that these two terms need to match. So we'll do a couple examples. I trust that you can use your calculator, and then we will be done. So give the setup and evaluate the integrals that give the volume of the solid by revolving y equals 4 minus x squared about the x-axis. So if I graph the line, or the curve, 4 minus x squared, we have a y-intercept at 4. We have x-intercepts at positive 2 and negative 2. And what I would like each one of you to do is draw in your representative rectangle. It doesn't matter where it goes per se, but that shows me what axis my rectangles are going to be perpendicular around. and then I'm going to indicate the axis of revolution. So in this case, the x-axis is our axis of revolution. This red line represents our representative rectangle. And our radius would be our upper function, so our curve, and our lower function. And in this case, everything is going to be bounded by the x-axis. So it may sound redundant to begin with, but it will pay off later if we consistently do this. So we're going to come up with our radius. It's our upper function, 4 minus x squared, minus our lower function. In this case, it's 0. Once we have our representative rectangle, then we jump to our volume formula. Our volume formula is pi integral left endpoint to right endpoint. So in this case, our left endpoint is -2. Our right endpoint is +2. Our integral is our radius function squared dx. So in this case, our radius function squared is 4 minus x squared squared. What I need from you guys in each one of these is draw the picture, give the radius, set up the volume. And once you do that, all you have to do is plug this into your calculator. And if you do that correctly, you're going to get 512 over 15 pi, or about 107.233. Either one of these is acceptable. And because there's no units, we don't put units on there. What happens if we turn this rectangle on its side? So here we have a second example. Set up and evaluate the integral that gives the volume of solid by revolving x equals -y squared plus 4y about the y-axis. So in this case, we have our y-axis, and that's where our curve is being revolved around. If we want to find the y-intercepts instead of the x-intercept, I can always set x equal to 0, because that's the y-axis, equals -y squared plus 4y. If I factor out the GCF, I get -y parentheses y minus 4, or my two y-intercepts in this case are going to be 0 and 4. And we can probably bet that the vertex here would be 4, 2. Now we are going to draw in our representative rectangle, so let's use the exact same color. It doesn't matter where this goes, but we are drawing this in to figure out what we are perpendicular to. So in this case, we're perpendicular to our y-axis. So our radius is going to be in terms of y. And if it's in terms of y, what we're going to do is the right function minus our left function. So our right function, rightmost function, is what we started with, -y squared plus 4y. And our left function is, again, 0, because that's our y-axis. So this gives us our radius. And now we are finding the volume. So let's do that in the same color. Volume equals pi integral. Now, in this case, we go low to high. So it would be 0 to 4 of my radius squared dy. So my radius squared is -y squared plus 4y dy. Notice that these match again. And if you type this function into our calculator, magically, it is the exact same thing as the first problem, 512 over 15 pi, or about 107.233. So we drew our picture, we set up our representative rectangle, we used the representative rectangle to find our radius, we plug our radius function into our volume formula, and then we let the calculator do the rest of the work. So I have one more question for you. And in this time, instead of revolving around the x-axis or the y-axis, we're going to be revolving around the line y equals -4. So find the volume of the solid formed by revolving the region bounded by 3x minus x squared and -4 about the line y equals -4. So let's draw in our parabola, and we'll draw in our line y equals -4. What we are spinning around our axis of revolution, which I want you to indicate, is -4. What I do need to find is where does my parabola intersect my horizontal line, because that will give me my bounds of integration. So to find the bounds of integration, I'm going to set these two functions equal to each other. I'll say 3x minus x squared equals -4. These are my two things that I want to solve for. So I'm going to set that equal to 0 by moving x squared and 3x to the other side. So I have x squared minus 3x minus 4 equals 0, which I can easily factor. Numbers that multiply on -4 that add to -3, -4, and +1. So my intersection points are 4 and -1. Now that I have my intersection points, I'm going to find my radius. So what I want is my upper function minus my lower function. Let's do that in red. I draw in my representative rectangle. We see that it's perpendicular to the x-axis. So it's going to be in terms of x. We have r of x is equal to, our upper function is our parabola. Our lower function is our horizontal line, so -4. So our radius in terms of x is going to be 3x minus x squared plus 4, which means we can jump to our volume equation. Volume equals pi integral. Left bound is -1. The right bound is 4. Our radius squared dx is going to be 3x minus x squared plus 4 squared. Pi r squared dx is our width. And if we integrate that using our calculator, we're going to get 625 pi over 6. So this gets us started for the disk method. And next, we are going to talk about the washer method, and that's included in 6.3 day 2.